Part 2. Many elements, their names are derived from Greek, Latin, or German words that describe a property of that element. Basically the language that science was being done at during that time period. And so we have the Greek Empire, and a lot of good science was done in the Greek Empire. And so iodine comes from the Greek word iodes, meaning violet-like. And iodine is violet-colored as a vapor. We have a lot of words in Latin. The Roman Empire spoke Latin, and they were here for over 1,000 years, and so a lot of good work was done in Latin. And even today, especially in medicine, Latin words still persist because Latin was used for so long. For a long time, it was the language of educated people. All academic things were done in Latin in Europe. All religious things were done in Latin. In fact, I think Latin used in Catholic masses existed until the late 1960s in the U.S., and so Latin was used a lot for a lot of purposes, which is why it's still here with us. Later, Germany was the most advanced country in chemistry. And so a lot of chemists take 3 semesters of German, because there are definitely some times as a graduate student when you need to look up a paper, and it's in Chemische Berichte or some other German stack journal in the chemistry basement, and you've got to look it up and translate it. And Google Translate will only take you so far with a scientific paper. It is immensely helpful to at least understand the basics of a language when you're using a mechanical translator to figure out what it means when you're trying to figure out what a chemist did. And a lot of the good basic work of the late 1800s up to World War II was done and published in German. Anything after World War II is typically in English, because that's about the time period in which English became an international language across the world. And so even these days in Germany, the top chemistry paper is published in English, just because if it's published in English, you get more viewership, more readership, the work is seen by more people, because a lot of people around the world either speak English as a first language or learn it in school as a second language. And so it's a useful common language for scientists, much in the way that Latin was back before. Some elements are named for the location of their discovery, like germanium. Some others are named for places, like californium. Some are named for people, like curium for Marie Curie, or einsteinium for Einstein. Each element will have a symbol. It'll either be 1 letter or 2 letters. If it's 1 letter, it will be capital. If it's 2 letters, the first will be capital, and the second will be small. And the small is important. If you write everything capital, it can be confusing. So capital N for nitrogen, capital A, small u for gold. And we will talk about why it's AU instead of something that starts with a G in a little bit. So here is where we're going to talk about it. So antimony, the symbol is SB for stibium, its old Latin name. Copper, Cu from cuprum, its old Greek name. Gold, AU, like we just saw. Aurum from Latin, AU. Iron, Fe for Latin, ferrum. Lead, PB for plumbum, which I believe is where the word plumbing came from, just because they used lead pipes back in those days. Mercury, Hg, hydrogerum, which kind of meant a watery silver in Greek. Potassium, K, German language, kalium. Silver, Ag, Latin, argentum. Sodium, Na, Latin, natrium. Tin, Sn, Latin, stannum. Tungsten, W for German word wolfram. And so, when the symbol does not make sense to the English name of the element, it's because this symbol is being derived from an earlier name for that element in the previous language that was dominant in chemistry at that time. Again, cobalt, capital C, small o. If you put them both capital, you would confuse someone. They would think you meant carbon monoxide. Capital C for carbon, capital O for oxygen. So again, the small letter is absolutely essential. The first letter is capital, and if there is a second letter, because there is not always a second letter, but if there is a second letter, it must be small case. And here you have the periodic table. Group 1 gets the nickname the alkali metals. Because if you put lithium or sodium or potassium into water, they completely dissolve, they burst into flames usually, and they leave the water basic or alkali. Alkaline earth metals means the metals form basic compounds, but the word earth means they don't dissolve in water, they stay solid. The halogens, fluorine, chlorine, bromine, and iodine are the halogens. Typically when someone says halogen, they're talking about some sort of light bulb. Halogens are used as a catalyst. Basically, old school light bulbs, back before LEDs and back before fluorescence, back in the days when it was an incandescent light bulb, those light bulbs worked off of black body radiation. If you've ever put an iron poker into a fire, you'll notice that after a while, it's hot enough to glow red, and that's black body radiation. Everyone you know has black body radiation. It's just that black body radiation is determined, the frequency and wavelength of light emitting from an object is based off of its temperature. So people are glowing in the infrared range. If you had a heat camera, you would see people glowing because they're emitting infrared light. The heat is leaving their body. When something gets a lot hotter, it starts emitting visible light. And that was really the purpose of those old school light bulbs. That little metal filament would get so hot that in addition to the heat, because you could easily burn yourself on an old light bulb, there was heat there, but it emits a lot of visible light. And so basically the theory of those first light bulbs was to put a metal filament inside of a glass case and fill it with an inert gas so that the metal filament doesn't just burn up, and then put so much energy through it that it gets so hot that it emits tons of visible light. Now that filament is so hot, it's slowly evaporating away. And so light bulbs go bad after a while because the tungsten evaporates and deposits on the glass. And usually you can see where the metal dust was depositing. But with a halogen, the halogen binds that gaseous tungsten and puts it back on the filament. And so because you're replacing your filament, you could actually run the light bulb a lot hotter, which meant the halogen light bulbs were a lot brighter. And so they were used in car headlights for that purpose. And so that is why we use the word halogen with light bulbs. And then there are the noble gases. Helium, neon, argon have never chemically reacted ever. Krypton, xenon, and radon have extremely limited chemistry. Xenon has been investigated as a possible anesthesia gas in certain specific brain surgeries. And radon is radioactive, so it's actually really dangerous. And you have to check your basement when you buy a house to make sure it doesn't have radon, because radon is one of the leading causes of lung cancer if people are breathing it in. And so it's good to know you have radon in a house because it's relatively easy to ventilate a basement, to ventilate it and get that radon out of there. But if you don't know you have a problem, you can't fix the problem. And so that's why testing for radon is a good idea, because if you do have a problem, it's a relatively easy fix, and so you can avoid a lot of problems later on with your health. This class is all about the representative elements. On the left, we have 1A and 2A. And on the right, we have 3A through 8A. In the middle of the transition metals, these are really for inorganic chemistry, which is a third year chemistry class. You take it, if you're a chemistry major, you take it in your junior year. This class doesn't focus on that. This class focuses on the representative elements. And here we see most atoms are metals. The easiest way to learn which atoms are metals, metalloids, and nonmetals is learn the metalloids. There's 7 of them. There's boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. Honestly, no one knows what 116 is. Only 2 or 3 atoms have ever been made, and it's so radioactive they decompose before they can even prove that they were made, and so we know nothing about it. And so don't worry about those heavy ones, like 115, 116, 117, 118. Nothing is known about those whatsoever, and so those aren't really relevant when we talk about chemistry. So we have the 7 metalloids. Again, boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. Everything to the right and hydrogen is a nonmetal. Everything to the left, besides hydrogen, is a metal. And so by learning the 7 metalloids, you all of a sudden know, with those 2 simple rules, every single atom. And that's the best way to learn them. So metals are solids at room temperature, except mercury. Mercury is a liquid because of relativistic effects that we talked about earlier. They're shiny. They're good conductors of heat and electricity, and they're malleable, which means that you can, if you hammer them, with a hammer, they don't shatter. The shape changes. And so anything that if you're beating it with a hammer, it's just denting and moving around, is malleable. And they're ductile. We can draw them into wires. Most metals have high melting points and densities. Again, mercury is an extreme exception. And common metals include aluminum, gold, platinum, silver, tin, and iron. Metals combine readily with nonmetals to form compounds. They rarely combine with other metals, but one exception is mercury. Mercury will dissolve other metals to form amalgams, which is why early dentistry used mercury. Mercury is not good for people, and so that's why dentists don't use mercury in fillings anymore. But before, it was the only compound that works, because when you're making something for a tooth, you have to make sure it expands like a tooth expands when you eat hot food, and it has to contract like a tooth contracts when you eat cold food. If it's contracting and expanding differently, it's going to be extremely painful and break away. So mercury was used because it was the only type of compound with the amalgams that worked for old school dentistry. These days, the material science has exploded, and there are many, many different resins and materials that work way better. And so the mercury is not needed anymore. But from a historical perspective, there was a time period where it was essential. Some metals are found in their free states. Copper, silver, and gold can be found free because they're super inert. None of them react with oxygen in the air. And again, this is why copper, silver, and gold have been used in coins for so long. Because those coins, once minted, they last a really, really, really long time. And so they're a useful currency. Some metals are mixed to form homogeneous mixtures called alloys, which we'll get back to in chapter 14 because these are solutions. But brass, that is copper and zinc, and it is very corrosion resistant. Bronze, copper and tin, very workable. Steel, iron and carbon, makes it much harder. And the coinage metals. Modern day coins are like cupro-nickel alloys. Nonmetals are not shiny. They have low melting points and densities and are poor conductors of heat and electricity. So they're brittle. If you hit them with a hammer, they will shatter. Nonmetals combine with each other to form molecular compounds, and they combine with metals to form ionic compounds. And here we see a miner carrying a load of sulfur. Metalloids are in between metals and nonmetals, and they have properties in between metals and nonmetals. And they are the 7 metalloids that we just showed you on the periodic table. Some of them are really important. Silicon and germanium are semiconductors and are completely essential to modern electronics. So what is the symbol for silver? Well, silver was Ag for argentum, the Latin name for silver. Which of the following are metals? Sodium. Yes, sodium is a metal. Molybdenum. Yes, molybdenum is a metal. Chlorine is to the right of the nonmetals, or of the metalloids. It's a nonmetal. Sulfur, nonmetal, is to the right of the metalloids. Magnesium's a metal. Platinum's a metal. Krypton, noble gas, nonmetal. Iodine, it's to the right of the metalloids, nonmetal. Carbon, to the right of boron, nonmetal. Copper is a metal. And so sodium, molybdenum, magnesium, platinum, and copper were the metals. The other ones were the nonmetals. Again, everything to the left of metalloids besides hydrogen is a metal. Everything to the right of the metalloids plus hydrogen is a nonmetal. Elements tend to be reactive and combine with other elements to form compounds. So it's really rare to find elements in their pure form in nature. You typically find them in minerals. Gold, silver, and platinum can be found pure, but in general, elements are found completely combined in minerals. And that brings us to the field of metallurgy. In metallurgy, you figure out how to extract a metal that you want out of a rock. And so how do you get the lead out of galena? That is metallurgy. Geologists figure out where to find a huge chunk of a mineral. Metallurgists then figure out how to purify the lithium or the lead or the copper or whatever you're looking for out of the mineral.